Okay, so last time I sort of suffered while solving this question. Where did the question go? Yes, this question. This is question 4, I think. Yeah. Um, and so we had to deal with CP, CV, and a lot of stuff basically. And the Maxwell's relations were the only thing that you could like really use in this whole scenario. And so I was pretty much done till the like first three equations, and now we just want to be expressing Cp and Cv in terms of T, V, alpha, Kt, and Ks. And so just to you know once again, like, just remember that Cp is essentially just um, it's just T ds upon dt at constant pressure. And you have this equation, and temperature and volume are like natural variables. Alpha thing is just uh, it's partial V by partial T at constant pressure, and then 1 upon V over there. And then Kt and Kv are just given by this quantity 1 by V partial V by partial T at constant temperature. And so I didn't have any sort of strategy to be solving this, right? As in, I was just like trying to figure out some way to mash everything together, and I realized that that's not a very good way of doing it. And so I think now I have a strategy. What we'll try to do is we'll try to eliminate one particular variable, and the variable of choice that I'm going to eliminate is entropy, right? um, yeah, I think so. I think eliminating entropy is a good idea. It could also be eliminating pressure, but that's in 3 places. Volume is also in 3 places. In fact, 4 places. That's not a good idea. Temperature is once again everywhere. So 4 places, not a good idea. So then the only thing remaining is entropy, and so we're going to eliminate that. So the way that we eliminate this is basically by switching these two terms. But of course, partial s upon partial t is an unnatural thing, so we can't just deal with it directly. So we introduce this new thing um, to help us. All right. So this is something that we do not really care all that much about because it's already P in PV and T. So we just need to cancel this entropy term from there somehow. Also, any other? Yeah. Okay. This is another scenario. So you should have a pressure over there, and then you should have partial S1 partial partial P1 partial T at constant volume. So the whole idea is to get rid of these terms, right? Yeah. Over here as well, this entropy term will first bring it inside, and then once it's inside, we'll cancel it with something else, right? Okay, so first let's try to deal with this term. So it just has pressure and entropy. Just think about it. So remember, you just have instead of like writing del p by del all of that stuff, I'm going to be using a new notation. So I'll just say p sub s, right? So the derivative of pressure with respect to entropy at constant volume, or something like that, right? So yeah, that's just what I'm going to do. So let me just write that equation again now. So p sub x and p sub y, v sub y minus this term Alright, and now what we'll do is we'll set x to be equal to p, y equal to s, and just see what happens. So we'll just have v sub s minus t, okay, that's pressure, that's y equal to s, so this is just there. So minus t sub p, sorry, yeah, alright, that's the thing. And that's equal to, so yeah, this whole thing is 0. So you just have this term. At constant, I think pressure, yeah, is equal to partial T by partial P at constant entropy. Cool. And so does this help us? Yeah, well, so it helps us because now you have partial T upon partial P at constant entropy, right? And so we can, once again, P and V is actually sort of an unnatural term, so we'll have to switch that up in any case. Cool. So we should be writing it like this. most probably. And so we already know this term, we just need to also figure out what this term is. Cool. So this we can already replace by partial V by partial S at constant pressure. All right, and now we want to be eliminating this somehow. Okay, so we want V sub t. So once again, like x equal to p, now we'll have to say y is s or something. Okay, that's sort of unnatural, isn't it? Yeah. So essentially we'll have to do partial t upon partial v, right? So we'll have to use instead of ps and we'll just use v and s. So then this just gives us okay, so y is s, so this term is gone. So minus t sub x is t sub v, and that's just there. So minus t sub v, that's equal to, so y is s, and then yeah, this is the term. So we essentially just have minus partial t by partial v at constant entropy. It's equal to partial p by partial s at constant temperature. Cool. So we can switch that up and just say that partial v by partial t at constant entropy is just partial s upon partial p at constant temperature. Right. And so there it goes. Partial s upon partial, and a negative, right? So just slash that up. So this just becomes partial s upon partial p at constant temperature. Cool. So far we're making progress, I think so. So now the issue is, how do we get rid of these s quantities somehow, right? Okay, so what I'm going to do is, like, I'm going to switch the p and t over there, and hopefully that will help in some way. Yeah, I think so. Yeah, right, it probably will help. Cool. Over there as well, we'll actually be switching up these quantities, the p and v, right? Okay, so p and v are actually also sort of not a good choice. So we can introduce a t over there, and then we can write this whole thing as partial. Okay, so we can't actually use t because partial s upon partial t does not make sense. Okay, so we'll actually just have to switch that up. There is no escaping that. So we'll switch that up, and we'll switch p and t from here, and hopefully that's gonna give us what we want. Yeah, I think that makes sense, right? Yeah, okay, so let's just get to work now. So first you want to be switching up this term, partial s upon partial p. So put x equal to p and y equal to t, and let's see what we get. And so putting that, so you just get v sub t minus t sub x is p, so that's like gone, and that's, so this is equal to that, and this is equal to, so p sub y is p sub t, and okay, so that's v sub x is p over there. Okay, so that term is gone, right? Yeah, I guess. Okay, it looks correct to me. So that term is gone, and it's now just minus, so you got t sub y is t sub t, that's 1 s sub p over there. Right, so essentially what you have is that partial s upon partial p at constant temperature, that can be quite conveniently written as negative partial v upon partial t at constant pressure. And so we are making progress so far. And so once again a negative sign is introduced, but now this is much better. So what you have is partial v upon partial t at constant pressure. Cool. Amazing. Okay, so another term that we got rid of, and so now we just need to get rid of this term. Okay, let's see if there's any simpler terms that we can get rid of. So we also have to get rid of this and that, right? Okay, how do we do that? So S by V, right, constant pressure. So we'll have to switch the pressure volume term. That's. Hey, wait a second. I see something. Yeah, I see something. Ah, I get it. I kind of get it. That's okay. Ah, yeah, right. Right. That makes sense. So this is like P and V. This is also P and V. Not very nice, but hey, what was that before we replaced it though? Like before we replaced it, it was this. Okay. Why is that constant temperature though? Oh, because we changed that, right? Yeah. So this is the new term. Okay, cool. No problem so far. It's just that I noticed that partial S by partial V at constant pressure is also available over here. So we could potentially be exploiting that. Right. Partial V by partial T at constant pressure. That's... Oh, okay. This term is just alpha. Well, that's nice. So we already have one thing that you could just exploit directly. Because this term is very much just this. Yeah. And then you can just divide that. Hey, what? Okay, that does not make sense. But there has to be some sort of catch, right? Wow, okay, this is crazy. So if I just do alpha upon ks, what do I get? I just get this partial s upon partial v term, right? Yeah. Okay, damn, that's very weird. I was not expecting it to be that simple. Did I make some sort of mistake somewhere? Yeah, okay, did I make some mistake? Could be. Could be a very big possibility. Volume, temperature, and pressure, right? It's entropy over there. That's okay. Not good. Partial V or partial S at constant pressure. Why do I just keep deleting these equations though? I probably should not be doing that. So I'm just going to write these equations in like shorthand. So just say V sub T at constant pressure is just negative S sub P at constant temperature. Cool. Okay, that's one thing. So you did that obviously. Constant pressure, right? That's for... So initially it was just S sub P at constant temperature, I suppose, right? So it was just partial S upon partial P at constant temperature, and this negative was not there. I'm assuming that was the case. Yeah, I think so. Cool. Wait, okay, that doesn't even make sense. Sorry, it should be pressure over there. Right. Yeah, so you changed this pressure term over there and then temperature term over there. Most likely that's what led to this happening. Yeah, so we should probably be writing down all the Maxwell equations first and then worry about all of that, so that things are better that way. Okay, so x equal to p and t we already did. Let's also go for x equal to p and v is probably not a good idea. So how about so since we just want terms with entropy in there, so wait, why did we do x equal to p and t though? So that we can switch that up, fine. But anyway, so we should also be doing the entropy volume term, or the entropy pressure term. That's sort of better. Cool. I think so, yeah. Entropy and pressure, I mean that's the scenario, right? So just have this term is gone, just got minus t sub x is like s. Well, okay, that's actually gone over there, and so just get like p sub s. Well, that's... wait, what? This doesn't even make sense. Okay, y is p, and that's... so it's just v sub s minus t sub y is pressure. So that's equal to 0, right? This is the equation. So basically you're saying like V sub S at constant pressure, that's equal to T sub P at constant entropy. Okay, that makes sense. That's another equation, and we sort of must have used this to get this. So it must have been like partial T by partial P at constant entropy first. Yeah, okay, that makes sense. Once again, we don't actually want constant entropy terms, so it's just better that way, I suppose. And we must have also done the pressure temperature stuff, so that this would make sense. I think so. Okay, wait, not a pressure temperature, but temperature entropy. What? No, that doesn't even make sense. Uh, yeah, how did we even come to this? What the? No. No, entropy and temperature. That would not be giving us the nice thing that we've got there. Something is problematic over here, isn't it? Okay, let's actually start over. What's K sub S? K sub S is partial V by partial P at constant entropy. And so you can write that as partial V by partial, just the other variable, which is T at constant entropy, and partial T by partial P at constant entropy. Right. Sorry. Right. I think so. Yeah. Partial P by partial V is probably not a term that you can ever get. So the only way is you use S and T. Okay. That ain't nice. The other way to be doing this probably would just be to use entropy is constant, but I don't think you will ever get this term, will you? So I suppose S and P is what must have given this. So constant temperature and pressure. Oh, okay, this is actually just this term, right? So that's what you changed this with. And what about this term though? At constant entropy. So it must have been the S and V term. Yeah, that's the only thing that makes sense for now. So doing that, the thing you would have probably got is something like but yeah, this is like much faster. That's the main point. So just P sub S at constant volume, that's equal to yeah, just equal to T sub V at constant entropy. Yeah, right. It's correct. Yeah, cool. So you must have used that to convert this. So we can just use, like reciprocal. You can just write reciprocals over there. So it just becomes V sub T, and this becomes S sub P. Right. So that's what I must have written there, like S sub P at constant volume. Yeah. And that's right. V sub S at constant pressure. Cool. And so now the only term remaining is to, well, just figure out what is this when we like switch S and P. We've already done that actually. Okay, when we switch P and V, right? Ooh, P and V is not a good idea, is it? Yeah. But that's just what you'll have to do. So this is just S sub P and yeah, okay, just write that over there. So what do you get? V sub T at constant entropy is just this quantity, right? So it's just partial S upon partial P at constant volume, and then this stuff just gives us this stuff. So V sub S at constant pressure. So making progress so far. Okay, cool. So you can use this in quite a lot of different ways, I suppose. Yeah. So our whole idea is just to eliminate the entropy term, right? Yeah. So notice the PV and T relations are already given to us essentially, right? So we could like exploit them for all we really need. Like first you notice that the p and t thing, using the cyclic relation we can just completely convert it. And so really we just need to get rid of this term and this term, and but both of these terms are already given to us using this and using okay, yes, actually we have to get rid of this term as well, because yeah, obviously. So v sub s at constant pressure. Yeah, so we'll have to switch pressure and volume for this to be gone, I suppose. Yeah, that's just the only thing that you can really do. Oof. So here we go. Yeah, here we go. So x equal to pressure, y equal to volume, so just get 1 minus. Yeah, I hate this, but there's no other way, huh? Oh wait, there is another way. There is another way. So rather than doing all of this, you can use the fact that oh it's actually not that bad apparently. Okay, cool. I get it. So previously I wrote a temperature term over there, didn't I? That makes sense. That's why I thought this would be so much solvable. It's not. Okay, because otherwise I would have solved this last time. Right. So now what we can do is, we know how to get partial s upon partial p at constant volume because we have this equation, and we also know how to get this term because we have this equation. So you can use these two equations and then plug that in this ks quantity. Yeah, and I bet that's gonna give you some nice things. You also have this quantity which we can simply write using alpha v. So I'm just gonna use this alpha v thing to rewrite it. This just becomes alpha times v. That's a temperature over there, by the way. Okay, also like this quantity can be written as, so negative, so okay, just think about it. You would have temperature upon volume, right, equal to that. Cool. So you just have a volume and okay, I just have to write that down. So you just have temperature and pressure, I think. Yeah, right. So T sub P at constant volume, and then P sub volume at constant temperature, and then V sub T at constant pressure. That would be equal to -1, I suppose. And so since this thing is P sub T at constant volume, this goes over there and we just get minus P sub V at constant temperature and V sub T at constant pressure. So it's just minus partial P by partial V. So this whole quantity can be written differently. This can be written as minus P sub V at constant temperature. I think that's the scenario. Yeah. And V sub T at constant pressure. Cool. So this is just one chain rule identity that we are going to be using. How do I select this? Cool. So we have used this identity, but I've noticed that the V sub T at constant pressure term, that's just once again alpha V. So you can write this whole thing as alpha V. Also notice that the P sub V at constant temperature term, that's something. So why is there a negative over there? Yeah, okay, that negative should in fact be there. So okay, the negative P sub V at constant temperature term, that could be just written as, what, 1 upon kT. So 1 upon V kT in fact. So just use that. Cool. Yeah, right, that's going good so far. So this V cancels with that V and you just get alpha upon kT over here. Right, I suppose there was a V, right? Okay, yeah, okay, there was a V. Fine, so we just get alpha upon kT. That's the scenario. Cool. uh, so far we're making progress. Cool. So you've got that now. Now it's pretty easy to see what we're supposed to be doing. Yeah, actually, yeah, this isn't too hard to see. So we already used these two equations to basically like substitute everything else. So now everything just using these two quantities, S sub V at constant pressure and S sub P at constant volume, right? So we can just delete these and nothing would be problematic. And so yeah, the whole idea is we just reduce the number of variables as much as we can. At least reduce the number of variables in the subscripts, because that will certainly help. Like, try to boil down everything to pressure, volume, temperature. Never leave anything else. So anyway, now this is very easy to see what we are supposed to be doing, right? So yeah, just divide. Like, just divide Cp and Cv. What do you get? So you get S sub v, or okay, let's just do Cv upon Cp, whatever. And so you just get S sub P at constant volume times, well, alpha is just gone, so that upon kT verticals of this thing, S sub V at constant pressure, we got 1 upon kT. You divide it, so also have this volume term, right? Now S sub V at constant pressure, that's okay, S sub P at constant volume, that's there, and then this stuff is just, yeah, exactly the same. So this just becomes Ks, so it's just Ks upon kT over there. This whole thing is just Ks. So what we have proved is that Cp upon Cv is just Kt upon Ks. Alright. And in fact, using this, we can directly complete the whole thing, because we already know what Cp minus Cv is, right? Yeah. And so this was really helpful to convert everything in a single, system. Like, system, I should say, using just three variables, like pressure, volume, temperature, convert everything to that, and things will just pop out themselves. It seems that's just the best way to be doing this. Yeah. So it's sort of elimination of variables, if you will. So you have this equation that Cp upon Cv is just Kt upon Ks, right? And this like also implies that Kt is sort of bigger than Ks, but well, whatever, just move on. And we also know that Cp is equal to Cv plus this whole quantity Tv alpha square upon Kt. And so we can use this to get the whole thing. So this is equal to this times of Cv, and so we can put that in there. We just get Cv times Kt upon Ks minus 1 is equal to this whole quantity Tv alpha square upon Kt. And so put that in the denominator, so Kv is equal to Ks upon Kt times Tv alpha square upon Kt minus Ks. Amazing, isn't it? Yeah, right. Looks cool to me. So then, now using this, you can just get what Cp is, because that's just Kt times Kt upon Ks times this. So you get Cp is equal to Tv alpha square upon Kt minus Ks. Amazing. These are our two results. I do not know about the validity of these two equations. They might be completely wrong, but as far as this is considered, we have solved this. Next, prove the following useful thermodynamic relations. So instead of energy, they're using U, but whatever. So partial U by partial V at constant temperature is just temperature, partial P by partial T at constant volume. So I'm gonna write it using energy E, but you're free to do whatever you want. So it's constant temperature is equal to temperature partial P by partial T at constant volume minus pressure. That's weird. At constant temperature, huh? Isothermic. Yeah, that doesn't make sense. How does that even add up? At constant temperature is Tt. It's not. So you're thinking of energy as a function of temperature and volume, are it not? Yeah, right. So I'm gonna prove his identity somehow. At constant temperature. So how does this change as you change the volume, but you're keeping the top temperature constant? So you know that you just have dE equal to TdS minus PdV, right? So divide by dV, just get dE upon dV is equal to this quantity, just TdS upon dV minus P. But now what you want this is that, well, this should happen at constant temperature. So take a partial derivative basically. And yeah, so this is what you get. And so all we have to prove is that this quantity is equal to this quantity. Oh, come on, that's easy. So just volume and temperature, switch those and you should get this. This shouldn't be hard to do. So once again, just have P sub x, V sub y minus T sub x sub y. In this case, you just put x equal to v and y equal to t, and let's just see what we have. So just have P sub v and V sub y is just temperature. Well, that's gone. So yeah, okay, minus T sub x is T sub v and S sub y, so just S sub temperature. What the? Oh, okay, so actually this is gone as well. So 0 is equal to P sub y, it's just P sub t. Okay, this is 1 minus that's also 1 S sub v, right? Easy, obviously, because S sub v constant temperature, that's equal to this quantity. Yeah, so we are done. This was very easy. Next question. Okay, next we want to prove that partial N upon partial mu at constant temperature and volume is equal to n square kT upon V, where mu is the chemical potential. And alright, this is going to be problematic, isn't that right? Yep, this is certainly going to be very problematic. I don't quite like the mu stuff. I think the third one is easier. So H is the enthalpy, right? Okay, so writing Cp partial T by partial P at constant enthalpy. Okay, that's new. At constant enthalpy. Wait, can we actually solve this question? Partial T enthalpy. What the? Okay, let's actually try that out. So you know that dH is just du, which is just, you know, TdS minus PdV, but then that plus the derivative of PV, so that's just plus PdV, sorry, plus VdP essentially. Okay, that's what the dH quantity. So dH equal to 0 would imply that, okay, so it's just like T partial S upon partial P at constant enthalpy, that should be equal to minus V. So this is actually the only equation that you really have. Yeah, how do I make heads or tails of this? Wow, what the? Constant enthalpy, partial T by partial P. How can you do this? Constant enthalpy, and you want to figure out the variation of temperature and pressure, huh? Okay, come on, think about it. So just have that, sure.
Hello.
It's the entropy thing that you know. Yeah, that does not help. So yeah, sure, you know that the entropy is gonna change with temperature, but it doesn't really help it, does it? No. How do I solve this? So it's T times of that minus V. Partial T upon partial P at constant enthalpy. How does that even make sense? Yeah, so using enthalpy now, aren't you? Okay, so we'll have to convert our equation into something that involves enthalpy. Think about it. CP is something you can certainly write using that. That isn't a problem. So the constant enthalpy situation only tells you this quantity is gonna be there. Okay. Anything else? Nope, nothing else. Let's just try to figure out some stuff. So you can write it as partial T by partial S times partial S upon partial P at constant enthalpy. So this part is figured out. Now this is completely just this quantity. Like what's partial S upon partial T at constant enthalpy? Yeah, that's not very helpful, is it? Yeah, it's not. At constant enthalpy is a difficult situation actually. So how about I actually try to create a Maxwell's relation for this? Yeah, that's gonna be hard. But if I'm able to do this, it will be certainly useful, right? So we want to have some sort of relation between temperature, pressure, and enthalpy. Okay. So we don't want the entropy situation. Cool. Just have ds is equal to that stuff. So yeah, right. And then we just have a second derivative over there, and that's probably gonna give you the thing. Yeah, this shouldn't be so hard. We just think of enthalpy as being another variable, isn't that right? Okay, let's actually try to figure it out. So then you wanna eliminate that somehow, right? So you'll just be writing ds is equal to dh upon, okay, yeah, I suppose that's just how it should be done. So just 1 upon tdh plus, so not plus actually, minus vdp. And so now you can just say that, okay, so partial s upon partial x, so s sub x basically, like s sub x is just 1 upon t h sub x minus vp sub x. And so from there you can say that s sub xy, and that's just equal to 1 upon, so okay, just negative 1 upon t square t sub y h sub x, right, plus 1 upon t h sub xy, and then minus v sub y p sub x, some other stuff, right? So minus vp sub xy. Now these two terms will also occur in the other sort of thing, so like in s sub yx. So essentially what you will be saying is something like, so h sub x t sub y upon t square, right, plus p sub x v sub y, that should be equal to h sub y t sub x upon t square plus p sub y v sub x. So now what we want is with pressure and enthalpy apparently. Okay, so we'll just let our x quantity be the pressure and the y quantity be the enthalpy, and let's just see what happens. So h sub p, that's 0, so this whole term is gone. So now just have p sub x is p sub pressure, that's just 1. So just have v sub h. This is so confusing. V sub h at constant pressure, that's equal to, so h sub y is enthalpy, so that's just 1 over there, t sub x, so t sub p at constant enthalpy, right? Okay, that's something that we sort of, nice, that's actually cool. So this stuff upon t square plus p sub y is, okay, that's gone, cool. And so essentially what you just have is that t sub p at constant enthalpy, that's just t square times v sub h at constant pressure. We can just plug that in, right? Yeah, so just have, okay, come on, so cp and then v sub h at constant pressure is equal to this stuff. Amazing. Okay, yeah, right, I see some stuff now. So c sub p, sorry, okay, what's cp basically? It's just h sub t at constant pressure, isn't that right? You bet it is. So it's just t and then P sub T at constant pressure minus V, right? Interesting. Yeah, okay, something's wrong, isn't it? What is wrong? This minus 1 upon T squared, this term. Okay, what is wrong here? This looks correct to me. Yes, is T square H. So that T square is there, right? Okay, that T square should be there. V sub H at constant pressure, sure. But then C sub P is just H sub T at constant pressure as well. And so this thing is just partial H upon partial T, and that's partial V upon partial H. So we're just doing V sub T at constant pressure. That times of T square, that's equal to T V sub T at constant pressure minus V. No, this doesn't even make sense. V by, okay, what? No, this doesn't make sense though. But enthalpy is certainly, Cp is defined to be that, right? Yes. Yeah, it is defined to be that. So how does it even make sense? It's T sub P at constant enthalpy. That's that scenario. Sure. So what is wrong? Oh, I see. There should be an upon temperature term over there. That's messed up, isn't it? So you have this whole thing, but multiplied by V. I see. Okay, wait, not this term. So you have this upon temperature and this upon temperature. But once again, you also have to take this negative 1 upon T into account. And so you essentially just have minus Vpx, okay, actually plus, so V upon T square, and then Px T sub Y. Right. So that's where that extra term is coming from. And so the actual full equation would be something like this thing minus V upon T square P sub X T sub Y, and over here as well minus V upon T square P sub X, sorry, P sub Y and T sub X. And so now putting X equal to enthalpy and Y equal to the pressure, what you get is, okay, let's just actually write this down. So let's just see what you get. So you get 1 and then T sub P. I suppose that's the thing. So T sub P 1 upon T square plus, so P sub X, that's gone, okay, minus V upon T square P sub X. So P sub X is like, okay, just kills that together. Okay, H sub Y, that's gone. And so this is just equal to P sub Y. What's P sub Y? So it's P sub P. Okay, cool. So it's just V sub H at constant pressure. This is constant enthalpy minus this quantity. So just V upon T square P sub Y. So that's just 1, and then just got T sub H at constant pressure. Amazing. I get it now. So now that T sub P subscript H thing can be written as T square times all of this stuff. So just have T sub P subscript H is just T square V sub H subscript P minus V TH P. And so now we'll put that in there instead. So I'm just gonna copy this stuff. So it's all of that times Cp. And that should be proven to be equal to T V sub T at constant pressure minus V. Now we can use what like Cp really is. It's just basically, Cp is just H sub T at constant pressure essentially. Yeah, right. And so using that fact, you can pull this inside and just get something like, T square V sub H at constant pressure H sub T at constant pressure. Okay, why is there a T square over there? Something is messed up, isn't it? Okay, that's a t. But then shouldn't this be having a 1 upon t term? Uh, there's a piece of x and yeah, right. Everything actually has a 1 upon t term. I don't know why that is not there for some reason. So this should be actually 1 upon t. Yeah, that makes more sense. Certainly. Right. Over here as well, it should be 1 upon t over this, not just like t and not this. Cool. And so that's why it's just t over there, not that. Cool. Right. And so this just gives us t, v sub h sub t, yeah, all that stuff, minus v is equal to this quantity, and that's trivially true at this point. So yeah, we just derived a new Maxwell relation, and that's how we were able to solve this. And so this whole thing is also done. Yeah, so that's 2.5, isn't it? Okay, b part is remaining, I think. So kt is given as thermal compressibility. We want to prove this quantity. So let me just write it down in words. So just partial n upon partial mu at constant temperature and volume, that's equal to n square kt upon v. So n square upon v essentially, and that times of kt, which is given by this quantity. So we're just proving that this plus, so there's a 1 upon v involved. Okay, so it's only v squared over there now. This is what we want to prove. Okay, cool. Yeah, so the equation that we'll be using is just this equation. dE is equal to pdv minus, sorry, not tds minus pdv plus s dt. Right, now notice that everything's at constant temperature in any case, right? Yeah, so we'll just assume that the temperature, this is wrong, sorry, that should be plus mu dn. So everything is at constant temperature anyway, and so wait, at constant temperature, that ain't nice. Oh, so we should be adding ts to this thing, so then the thing is actually should be dealing with df in that case. So now it's just going to be minus s dt. Yeah, so it's at constant temperature, so this is like gone in any case. This term is at constant volume, right? And what about this term? Well, that's obviously at constant n, because that's just the way it is, right? Yeah, so the variables that you want to switch is now, it's now like v and n essentially, right? This whole equation we can also sort of write it differently. We can write it like d mu upon dn at constant temperature and volume plus e square upon n square. Yeah, right. At, and then n it's like partial p1 partial v at constant temperature and number of atoms is equal to 0, molecules, whatever. Cool. And so now it's very visible that we just want to switching v and n, right? Okay, so cool. In this case, you have this equation, so you just have f sub x is equal to minus pv sub x plus mu n sub x, right? And so you just get minus p sub y. I'm just gonna do it directly at this point. So just p sub y v sub x minus mu sub y n sub x, and that's equal to p sub x v sub y minus mu sub what was I going to say? I've forgotten what I was going to say. Wow. Yeah, I forgot what I was going to say. Can't believe this. Okay. Shit, I don't remember. P sub x, v sub y minus, oh, okay, right. So mu sub x and sub y. I'm getting sleepy, I think. Okay, so that is the thing that we'll be using. Okay, so now what we want to be inputting in this is just x equal to So one of them must be n, and then the other one must be this term, the volume term. And all of this has to happen at constant temperature. So just kind of don't like regard that for now. We have in mind that it's going to be a constant temperature. So now just plug that in and see what happens. So it's just P sub V, and okay, that actually kills that, so no. Minus mu sub n sub x. Okay, that's actually fine. So mu sub V at constant n, that's equal to, so you got P sub x, V sub y. Where is it? P sub x, V sub y. P sub n, V sub v. So that's just 1. So that's just P sub n essentially at constant y, which is v. Yes. Wow, I'm sleepy. Yeah. I need to rest, but I can't. So this is the thing that we're actually getting. This does not match with what we were given though. It's the chemical potential. Okay, whatever. So what we want is n sub mu at constant temperature and volume, right? Wait, n and mu are actually similar things. You can't be using them like that. N sub mu. What? How is that even going to be valid? Okay, so we just switched what and what? We switched n and v. Oh, come on, think. Don't just give the subs. Yeah, right. So we want n with respect to mu. That's an unstable thing. So we need to change that. So it's going to be actually partial n upon partial something else, anything else in fact. And so this is our equation. So I am supposing that pressure is something that you can use. So I'm just going to say partial P at some volume, and then just have partial mu upon partial. What am I writing? Partial P at partial mu at some volume, right? That's the way it should be. So we should have switched volume and pressure, and not n and v. Yeah, that's probably not a good idea, but we'll still just keep this equation. Yeah, I've learned from my mistakes. Now I'm gonna keep this equation. All right, so now we want to be dealing with pressure and volume, so just put x equal to p and see what we get. And so just get v sub well, why is that x? What? Oh, okay, this whole term is like gone actually. So it's got minus mu sub y. What? So mu sub v at constant pressure and n sub p at constant volume. It's equal to 1 minus mu sub p at constant volume. Why am I feeling sleepy? Okay, this has never happened to me before. I don't know, it's just I can't focus. So v sub, what is this? V sub v. No, wait, what am I? This is wrong. N sub y, right? So y is v, so it's just n sub v at constant pressure. Yes, that's how it should be. Come on, wake up. So you have, what was I doing now? Yes, we wanted to find out what this term is. Where did the term go? Okay, right. N sub p at constant volume, that's what we want to find. And did we find that? Yes, actually we did. This is the term, right? And so we kind of want to prove that this is equal to n square kt upon v, right? Once again, what's kt? Kt is just this quantity, v sub p. Oh, that's another problematic term. Why do these people keep doing that? I don't know. So we'll actually just have to write the whole thing first and then see if anything makes sense. Yeah. Wow, this sucks. This is equal to minus n square upon v square, and then this term can be written as partial v by partial. So you are doing it at constant n, so I suppose mu is what you should be using, and then partial mu upon partial p at constant n, I suppose. Yeah, this is what we want to prove. So far we've got two equations. So you got just like write this in a simpler form. So n sub p at constant volume and then p sub mu at constant v, yes, is equal to minus n square upon v square, v sub mu at constant n and mu sub p at constant n. Yes. Wait, why is it different? Sorry, it should be at constant volume. Yeah, okay, right, that's correct. So yeah, so mu sub v at constant pressure. So okay, the constant pressure term is not there anywhere. That's not a good idea. So we'll need to change this somehow. It's the constant volume term. Yeah, that's over there. So this can be written as p sub mu at constant volume, right? Okay. So this actually gives us something like, so this thing, in fact, this gives us n sub p at constant volume and then p sub mu at constant volume. It just goes over there, and that's equal to p sub mu at constant volume and v sub mu at constant pressure. I'm feeling really sleepy right now. I don't want to be continuing. Yeah, I don't want to continue this. I have no idea where this n square upon v square term is gonna come from. Yeah, I should take a break. Alright, so I'll see you guys in the next video. Bye.